Rolling.
Okay, so on some of your answers on the assignment that I just gave back, let's talk about this, okay? So, one of the questions, this is on the assignment, literally, it was like yesterday's assignment, I just gave it back. So one of it was like on question 51, it was, can, like, the chloride ion be reduced by aluminum, okay? So, here's the deal. So, the kind of the code here is that if you say, can chloride ion be reduced by aluminum, okay? So basically what you're asking is, can this chloride ion come up to the aluminum? Because the only thing aluminum can turn into is Al3+, okay? Well, go away. Stop. What did you do? Here we go. Okay? That's the only thing aluminum can turn into. It is a one-trick pony. It's a good trick, okay? But it's a one-trick pony. It can't turn into Al1-. It can only turn into Al3+. So elemental aluminum can only be oxidized. So the question is here's the $1 million question. Can Cl1- come up to the aluminum and take electrons away? Now, if that happens, what's going to happen to the oxidation number of the chloride ion? It's going to go to what? 2 minus, 3 minus something. It's going to gain an electron, right? And especially if it's from aluminum, it would have to gain 3 electrons. So you're going to tell me that Cl- plus Al is going to end up at Cl4- and Al3+. Have you ever seen Cl4-? No. You know why? Not stable. It's like, have you ever seen a cool freshman? No. It doesn't exist. So this can't happen. So if you look at Cl-, the only thing that you can do with Cl- is take electrons away from it and turn it into Cl2. Okay? So the idea that chloride ions could be reduced doesn't make any sense. Now, the same thing is true of Na+. Okay? So the question is can sodium be reduced by aluminum? So if that was going to happen, this at least has some realm of possibility. But the sodium would gain an electron, and it would turn into elemental sodium. This at least has the possibility of the sodium gaining an electron and taking in the sodium. But again, if you look at your E0 values, okay, if you look at where you're at on this chart, so you have Na+ would have to go in this direction, which is like negative 2.71. The aluminum would have to get reversed, and it would turn into Al3+. So you'd have a positive 1.66 plus, positive 1.66 and a positive, or a negative 2.71. You'd end up with a negative E0 value, and the reaction isn't spontaneous, okay? Now, here's the other one. The question is Zn2+ a good reducing agent? Okay, so let's think this through. If I'm asking if something is a good reducing agent, fundamentally what am I asking?
Does it oxidize?
Does it oxidize, which means what? Does it do what?
Give away electrons.
Does it give away electrons? Okay, that's the fundamental question. Does Zn2+ give away electrons easily?
It could.
Well, it could, but then it would turn into like Zn3+ or Zn4+.
And that's not really...
Probably not. Now, realistically, when you have charged elements, Cl-, Zn2+, whatever, those are 99% of the time at the bottom of like the energy well. That's when it's going to be most stable. The only exception is if you have Fe2+, because Fe2+ can roll one of two ways. It can turn into elemental iron, or it can turn into Fe3+. But generally, when you see a cation or an anion, Zn2+, Ag+, something like that, it's only going to go one of two ways. It's either going to, that's probably, if it's positive, the only thing it can possibly do is gain an electron and turn back into the elemental form. If it's an anion, the only thing it can do is gain an electron, is lose that electron and turn back into like chlorine gas or iodine or something like that. So, the rare exceptions is Fe2+. Fe2+ can turn into elemental iron, or it can turn into Fe3+. And the same thing with copper 1+. Copper 1+ can turn into elemental copper, or it can lose and turn into Cu2+. But most of the time, when you have an anion, the only thing it can possibly do is lose an electron, which means it can only be oxidized. If you have a cation, sodium Na plus, Zn2 plus, the only thing that can do, for the most part, is be reduced back into its elemental form. So that's the game that you kind of want to begin to think through. Okay, any questions on the assignment from yesterday? Jason?
Number 1. So, are these both oxidation reactions?
I mean, they're both redox.
But A,
There's-
Cr3 plus to Cr2O7.
Okay.
No, that's the whole thing.
That Cr would be 6 plus, so that would be losing electrons. With a Cl2 to Cl minus, that's also losing electrons. So that's a ox-ox reaction.
No, because look,
That doesn't exist.
your Cl2, right?
Yeah.
Okay. So you have Cr3 plus turning into Cr2O7, right?
Mm-hmm.
So if you look on this reduction chart here, where you've got the Cr2, right, turning into Cr, that value is 1.33, okay? So that's going to get reversed, and that's going to be negative 1.33. Okay, because if you look on your reduction chart, okay, the way it is written is you're talking about the reduction of Cr2O7. So we're going to reverse that, and we're going to make that the oxidation part. So that's going to be negative 1.33. Then you have Cl minus, or Cl2, directly up above it, right? That's going to go in that direction because that's 1.36.
Oh, that's being reduced.
Yeah, so the chlorine is getting reduced.
Oops.
The dichromate is getting oxidized, so that's in the reverse direction. So you're going to have 1.36 plus a negative 1.33. Does that make sense?
Yeah.
So then you get a positive E naught value, okay? And you get a negative delta G, and the reaction is spontaneous. So if your answer is in kilojoules on number 1A, it should, in kilojoules, it should be something around your current age. Okay, Ren?
How do you do 6C?
That's a good question. Okay? So on 6C, here's your setup. So will iron dissolve in a 1 molar solution of Ce4+. So here's how this would actually play out. Okay? You're going to have a solution of Ce4+ ions. Okay? Maybe it was CZ nitrate. You mixed it up. Okay? Boom. And what you're going to do is you're going to add iron to it. Okay? So you would physically add a chunk of iron into this. So the only way the iron can dissolve is if it gave up electrons. Okay? That's the only way that can happen. So what would happen is that you have Ce4+ and iron. Well, you know iron is not going to gain an electron and turn into like Fe1-. Okay? It's a metal. The only thing that it can do is lose electrons. So if you look on your reduction chart, right? So number 1, here's the whole key to this. You are starting with iron. You are not starting with Fe2+. You are not starting with Fe3+. You are starting with iron. So right away, if you look on this chart, okay, you do not see iron as a reactant on this reduction chart. You don't see iron. You cannot start with iron at all on this reduction chart. The only thing you can do is start with iron as a product and reverse it into something else. Okay? So if you look, you've got Fe2+, right? Plus 2 electrons turning into iron, and that has a value of, what is it? Negative 0.44 volts. So what's going to happen is that this is going to turn into an oxidation reaction. So the iron, when it gives up the electrons, is going to turn into Fe2 plus, and it's going to give up 2 electrons. So as soon as I reverse this, this becomes positive 0.44. Because now I'm going to look at it from an oxidation standpoint. Okay? Now, then you come up here and you find Ce4 plus. Okay? Now, Ce4 plus, where's Ce4 plus? Huh? Top left, okay? That's 1.70, okay? So here's the question. Does Ce4 plus really want to turn into Ce3 plus?
Yes.
Yeah.
Yes. So this is going to go in this direction. So if this goes in this direction, that's 1.70. So I've got 1.70 plus a positive 0.44. Is that going to give me a positive E naught value? Yes. So will it dissolve?
Yes.
Yes. Okay? Yes.
Can we, how many species should we have on 6D and
On 6D,
E? And E.
you're killing me.
How many, just the list of number of species?
3 on D
3 on D? Oh.
and 2 on E.
Oh no.
Okay, got that. Can we go over number 5?
Which part?
Like just the redox part, because it.
Chlorine dioxide, is that bleach?
Is that, hold on. Just, yeah. Just, okay. So number 5, okay? I've given you the reaction. It's NaClO2 aqueous turning into okay, so you've got the reaction, right? So on this one, calculate E naught and delta G for the reaction. So you're just going to go through on the chart and find the values.
So we don't need to make it. We don't need to find it as a redox reaction, or.
Well, it is a redox reaction. That's just it. Otherwise, you can't calculate E naught.
Okay.
Okay, that's the whole point of it.
But do we need to find the half reactions in order to get those E naught values?
You don't have to,
Okay.
but it's handy if you do that because then you know how many electrons are involved. Because if you don't know the value of N, then you can't calculate delta G.
So could we go over those half reactions? Because I was confused how chlorine is in each
Okay,
part.
so chlorine is unique in the sense that it's going to be both oxidized and reduced. So you have chlorine gas, right?
Mm-hmm.
Turning into Cl1 minus, okay?
Mm-hmm.
So that means it's going to gain 2 electrons, and you have this. So in this situation here, N is going to equal 2. So that's the easy one, okay? So this is why if you ever have a pool or swim in pools, right, it always smells like chlorine. Because chlorine is a very, very good oxidizing agent. It really wants to reduce. So it's going to take electrons from something, bacteria, whatever it is that you want it to destroy. And then that's why it works, okay? Because of the fact that it's going to take electrons from something. That's why you use chlorine in pools.
Interesting.
Yeah. Yeah, don't throw, oh, I want to clean my pool with gold. I want to throw gold in there. Don't, okay? Guess what? Gold isn't going to do anything, okay?
Just gonna look
But we
pretty.
throw salt in it. They're like salt.
Yeah, you can have like saltwater pools,
But
but that's a different,
Yeah.
okay, this is just if you typically use chlorine pools. Okay. Now, the other one is that you have ClO2, right?
Mm-hmm.
Minus turning into ClO2 as a gas. So here's the difference in this. As NaClO2, this whole thing has a charge of 1 minus. Over here, as a gas, it's ClO2 as a neutral molecule, okay? So over here, chlorine has a charge of 2 plus, okay? Because you've got 4 plus. Because you've got oxygen at 2 minus, and then you have the chlorine, right? So this whole thing has to add up to equal to 0, so it's 4 plus over here. Over here, you want this to add up to 1 minus, So you've got 2 oxygens, which is 4, so this means over here that chlorine is 3 plus. Okay?
Okay.
So the only way that can happen is if it loses an electron to become Cl4 plus on the other side.
Okay. Okay.
So if all goes well on your E naught value on 5A, that should be around 0.5. That's an ish, okay? And your delta G, if you do kilojoules, should be around negative 80. Okay? It's an ish, but it should be something around there. And the mass on B of your chlorine should be in the mid 400 grams. You like those answers?
I do, yeah.
Okay. All right.
Y'all are too good.
Can we go over 6D?
Go over what?
6D.
B?
D, delta.
D? Okay.
E times
So on 16, which of the species can be oxidized by H+, right? So here's the deal. Basically, what we're asking is which elements, when you dump them in with an acid, say it's hydrochloric acid, whatever, can this hydrogen gain an electron and turn into H2? Okay? That's what we're asking. Now, start with something that you know. Think of magnesium. Okay, let's just say magnesium.
I can't stop thinking about magnesium.
Okay, if you drop magnesium into hydrochloric acid, does it react?
Yes.
Yes. Okay, so think of one that you know. Okay, you know if you dump magnesium into hydrochloric acid, you're going to get a reaction, right? You know that's going to happen. So then, look at your chart in terms of a trend. Okay, hydrogen is defined as 0. Okay, so 2H plus, that's 0. Now, where is magnesium in relation to hydrogen?
above, it's 232%.
Okay, hold on. Where is magnesium on this chart relative to hydrogen? Above or below it?
Below.
It's below it, right? Okay,
Found it.
got it?
Yep, found it.
So hydrogen there, the hydronium ions, will react with anything that's below it. But it won't react with anything that's above it.
Right. Okay.
You can also look at it from E naught values. So if you look at magnesium down here, right, what would happen is the magnesium would give up its electrons and turn into Mg2 plus. That would be a positive 2.37 plus 0, which would get me a positive E naught value. Now, if you try copper, okay, if you go up above and you start with elemental copper, and if you tried to reverse that, that would be negative 0.34. That would be a negative E naught value, which means it's not spontaneous. So anything above it, it won't react with it. Anything below, it will. So that's why you can play like the over-under game.
Sure.
Okay? Does that make sense?
I think so.
Okay. Anything else on the assignment?
On 4 for both A and B, how do you get the joules per mole into joules?
What do you mean?
Because for 4 it's asking for a maximum amount of work, and work is joules, right?
Yeah, but it's joules per mole of the reaction.
Oh, so we can just leave it as
Yeah.
the joules per mole.
Yeah,
Oh, so I overthought it.
yeah, done.
Okay. Thank
So
you.
1B, would you like to?
So on 4, A and B, both of them, the last 2 digits should be 61 if you're in kilojoules.
Oh, okay.
Would you like to give us an estimate on 1B?
On 1B, if you're in kilojoules, it's the number of miles driven on a race held on Memorial Day weekend.
Hold on.
How do you know this?
Number of miles driven on a race?
On a famous race
Oh,
held on
that's,
Memorial Day
I got
weekend.
it. It's in Florida?
No,
No, what?
It's in Indiana.
The Indy 500.
Yes!
Oh, I thought you were talking about Daytona.
That's
just
Memorial
happened.
Day!
That just happened.
What?
The day, what kind of redneck are you? Serious?
They're both.
Memorial Day weekend, see Indy 500, come on.
I didn't know that.
They're also
did?
like, all of them end in 500.
No, they don't.
No. Most of them.
Pocono 400.
Guess I don't watch NASCAR.
Racing my redneck game.
Yeah, people who don't watch NASCAR.
Do you know how
You know
hard
what
it is?
NASCAR stands for? Non-athletic sport centered
Around
around
rednecks.
I'm sure
Whoa,
that's exactly what it
is it?
says.
And it-
No.
I know SC is stock car, but what?
You know, driving straight is actually surprisingly hard.
It's not.
Like,
For you, I have no doubt.
it's going right. What?
You have to.
Then you steer it back left.
Your line.
Maybe not that dramatically.
That's actually, cars are actually slightly designed to go to the right. And here's the thought process, is that if you fall asleep, they would rather have you go to the right
Uh-huh.
than go to the left into
So in
oncoming traffic.
England, they're designed to go to the left.
Yes.
Weird.
That's what I was
Now, that's
Okay.
theoretical. Most of the time, they just go straight in. But anyway. Okay, anything else on once or twice sold? Okay, get that handed
Gonna
in.
get me a Tesla and fall asleep at the wheel.
Yeah.
Did you hear?
No, I'm gonna turn on
Tesla
Netflix
say
in
the
my-
slide?
My Tesla.
Seen that Zach Fox movie
Tesla,
video?
why would
Being
you
kicked
say
in?
Tesla?
Tesla.
Okay.
Tesla.
Tesla.
Where's the
With a Z.
Tesla.
With a Z.
No,
I like my Z's, man.
that doesn't make it okay.
Tesla.
Tesla.
Tesla. I said it weird.
Tesla.
The first
is
time.
how
Hey,
you-
Nikola Tesla is a Sith.
Okay, now,
Yeah.
I emphasize this is a practice quiz. Okay?
No.
We're going to go over it. Okay? It's not for a grade, but this is going to give you kind of an idea of where you're at in terms of this whole idea of redox. So I'm going to give you about a half an hour here. And you've got, and this is what you're going to have. You're going to have both the big reduction table that I gave you, okay, and that yellow one. Mostly everything. I always go off of that big reduction table because that includes everything that's here. So, anyway, so here we go.
Oh.
Did I turn this off?
And you, like I said, you'd have your periodic table, you'd have everything else, but this is just going to